So question 1 is about the ionization energy of a noble gas neon, and looking at asking what the successive ionization energies of neon in a sketch is going to look like. Well, the first thing you have to be happy with is what the term ionization energy means, and it's the energy that's required to convert 1 mole of gaseous atoms into 1 mole of gaseous ions, each of them losing an electron. So this, because we're forming a 1 plus ion, would be the first ionization energy. You know that neon has 10 electrons because it's got an atomic number of 10. Therefore, it could theoretically have 10 ionization energies. So the 10th one, for example, would be Ne9 plus gas going to Ne10 plus gas plus an electron. So we have to think about where there are going to be jumps. So what you needed to do, even though it didn't ask you this in the question, was to draw the electron in boxes diagram for neon. And you know that it has 10 electrons, so therefore it has an electronic configuration of 1s2, 2s2, 2p6. So the first electron to be lost is going to be from one of the 2p orbitals. The second electron that's lost is going to be from a distinct 2p orbital. The third electron that's going to be lost is from a distinct 2p orbital. So therefore, each time you're losing an electron, but you're not losing a proton, therefore you're getting more positive. Therefore, the successive ionization energies are getting steadily bigger. So hence, in the first stage of your graph, it is increasing at a constant rate for the first 3 ionization energies. Then the 4th ionization energy, I'm going to remove one of these electrons from my 2p orbital. So in this case, I might remove it from my 2px orbital. Well, now that electron is unpaired. So therefore, it's going to exhibit less repulsion than it did before when there was the other electron there. Remember, electrons repel each other. So therefore, the energy required to remove that electron is going to be slightly higher. So therefore, I've drawn my 4th ionization energy slightly higher. Okay, slightly higher gradient than 1 to 3. You can see that there. Okay, again, my 5th ionization energy is removing these now unpaired electrons from my distinct py and pz orbitals. Again, therefore, that's going to take more energy than the first 3, so therefore my gradient is increasing again. Okay, so I've gone 1, 2, 3, 4, 5, 6. I've formed Ne6 plus. I've gone to my 6th ionization energy. So going to my 7th ionization energy, there's going to be a slight jump again, because I'm now going into a new subshell. Okay. But the big jump is going from my 8th to my 9th ionization energy, because I'm going into a new complete shell. And obviously now I've got less shielding. So therefore, if I've got less shielding, my ionization energy is going to be much, much higher. Okay, so my jump from the 8th ionization energy to the 9th ionization energy is more significant than any other jumps. Okay, and the next part of the question was asking you to explain this. So from the 8th ionization energy, you're going into a new shell, and therefore the outer electrons are closer to the nucleus. There's less shielding, and therefore it's more difficult to remove the electron, and therefore the ionization energy is significantly higher. In the second part of the question, it's asking you an AO3 question by giving you 2 compounds you've never heard of before. Now, lots of you said, when have we ever looked at ionic bonding in noble gases? And the answer is you haven't. But this is an AO3 question. It's asking you to apply knowledge that you have looked at to an unfamiliar scenario. So it's asking you to explain why it's not possible to make an ionic compound with argon, but it is possible to make the ionic compound with xenon. The reason is you need to compare the relative radii of argon and xenon. Xenon is much larger, and therefore it has a larger ionic radius. The attraction to the outer electron is going to be much, much weaker because it's further away from the nucleus. Therefore, it's going to be easier to lose that electron and form the positive ion, and therefore it's going to be easier to make an ionic compound. Okay, you could have also said that because it had a larger radius, its ionization energy would be lower, and therefore it's going to be easier to remove that electron and form the positive ion. Another example of an AO3 question was this next question, asking you what's happening in the atomic absorption spectrum. Again, you haven't studied this directly, but you have studied that different shells and different subshells have different energy levels. So if you've got something in the 1s or the 2s, for example, it can be promoted by providing that with energy. Okay, that means the electrons get excited and they go into an energy level of higher energy. Okay, they then at some stage have to fall back down. Okay, and they can fall back down to the ground state, but depending, and then as they fall down, they give out that energy again. But depending on how big the fall is, they will give out different amounts of energy. And that is seen with different frequencies, because the energy is going to be proportional to the frequency times Planck's constant. You might have met that equation in physics before. So how did I put this in words? Well, the element's heated. The electrons get promoted to orbitals of higher energy. The electrons, so that's my first mark. As the electrons fall back to the ground state, they release energy as light. Okay, and I also needed to state that the different orbitals have distinct energies. Okay, so depending on how big the drop was, you'd see this by different frequencies of light given off. I had to mention the word frequency for that second mark.